In this section we will have a closer look at the mobility procedures defined inside the LTE system. This means how the subscriber moves from one cell to another. This slide illustrates in a very simplified way the procedures for a handover from a UI between two base stations, a source eNode B or base station and a target eNode B or base station. Also the X2 interface between the two base stations is involved in this case. The mobility management entity is not changed. That means both base stations stay connected with the same mobility management entity or MME, so we have the case of an intra-MME handover. The MME is part of the Evolved Packet Core EPC in this figure. First of all, the UI is reporting measurements. This means neighbor cell measurements according to the measurement configuration provided by the base station, and the base station is then evaluating the measurement reports. The base station will decide about a handover in case, for example, a neighboring cell shows much better quality than the source cell. So this would be the handover decision. In case this neighboring cell belongs to another base station, we have an inter-base station handover, and the source base station will then communicate with the target via the X2 interface. The source will request a handover so that the target can do admission control and check whether it can accept the new terminal. In case it can accept the handover, it will send a handover request acknowledge message via the X2 interface. The target base station can then start the handover over the air interface. It is then sending the handover command to the UI, and in case of LTE, this is actually an RRC connection reconfiguration message. It contains all the required information regarding the target cell so that the UI is able to access the target cell. The UI can then detach from the source cell and synchronize to the target cell. And on the base station side, data packets, sequence number information can be forwarded from the source to the target base station again over the X2 interface, and the target can buff the new packets. As soon as the UI is connected then to the target base station, the RRC connection reconfiguration procedure is complete. And the paths between the Evolved Packet Core and the base stations can be switched so that the data path now goes to the new base station and all the new packets are delivered to the new target base station. So all the contacts, the UI contacts in the source base station can now be released, all buffers can be flushed, and all the resources can be released there. So there's not only intra-LTE mobility, but also LTE between 2G and 3G networks defined in the LTE. On this side, for example, the possible transitions between the LTE and GSM GPRS states, as well between LTE and wideband CDMA HSPA states are shown. In LTE there's only two protocol states defined on the radio resource control RRC level: the RRC connected and the RRC idle. These are shown in yellow here. And the mobility in RRC idle between LTE and the other technologies is done via cell reselection mechanisms. Mobility in RRC connected is done via handover procedures. For example, from the EUTRA RRC connected state to the UMTS cell DCH state, or from the EUTRA RRC connected state to either the GSM connected or the GPRS packet transferred mode state. In between LTE and GSM GPRS, you can see that also cell change order mechanisms, abbreviated CCO, are defined, also including network assisted cell change, NACC. Of course, not only transition from LTE to GSM Edge and wideband CDMA HSPA, but also between LTE and CDMA 2000 based technologies is required. And this is true for both the HRPD high rate packet data and for 1X RTT circuit switched services. And this figure again shows the allowed state transitions in terms of state transition between RRC connected and the CDMA states and RRC idle and the CDMA states. Note that CDMA 2000 messages are sent transparently to the UI over the EUTRAN, and the base station and the MME acting as relay points. All the described mobility scenarios we have just seen, for 2G, 3G, wideband CDMA, GSM, and CDMA are part of 3GPP Release 8 specifications. So these interworking scenarios, mobility scenarios, they are all part of LTE from the beginning. Now the next section will cover MIMO multi-antenna technology. MIMO is a key feature of the LTE air interface because it is needed to achieve the high throughput and data rate requirements for LTE. MIMO stands for multiple input, multiple output, because multiple transmit antennas are used that form multiple inputs to the radio channel, and typically multiple receive antennas are used, which are provided with multiple outputs from the radio channel. So a brief introduction to MIMO in general before we go to the LTE specific things. We've seen that MIMO basically means using multiple antennas at both transmitter and receiver side, but what are you doing with these multiple antennas? What are the gains to exploit? First of all, a diversity gain can be exploited. This is illustrated in the first figure shown here. By transmitting the same data streams over multiple transmit antennas, for example at a base station site, the receiver, which could be the wireless terminal, has multiple replicas of the same signal available. And so at the receiver side you can achieve a higher signal-to-noise ratio. This diversity gain is very efficient to combat fading over the mobile radio channel. However, the data rate cannot be increased because each antenna is actually transmitting the same information stream. You have actually more redundancy available. Note that typically the streams transmitted by each antenna are coded with an additional antenna-specific pattern to further increase the diversity effect. An example would be the space-time or space-frequency coding according to LMUTI. That is a very commonly used scheme. The next figure shows a slight difference, and it shows a simplified example for spatial multiplexing. And in this case, a multiplexing gain can be exploited by using the multiple antennas. And now each transmit antenna transmits a different data stream, S1, S2, and so on as shown here. And these streams are transmitted simultaneously over the same radio resources over the air interface. And this is possible by exploiting the spatial dimension. So by doing so, the data rate can of course be increased because now more data is actually transmitted over the resources at a certain point in time. However, of course, no diversity gain can be exploited. The transmission may not always be successful, and this really largely depends on the correlation characteristics of the mobile radio channel. If the channels that are formed between the transmit and receive antennas are highly correlated, then the performance of spatial multiplexing will deteriorate. So spatial multiplexing really works best in uncorrelated scenarios. And we really have a high dependency of the performance depending on the channel conditions, which is also the reason why spatial multiplexing typically is being tested in fading scenarios, and fading simulation is a very important testing feature for testing MIMO systems. In fact, it is also possible to switch between the MIMO modes, transmit diversity and spatial multiplexing, and this is also done in LTE. The decision which MIMO mode to apply is taken in the base station based on the UE feedback received. So MIMO is typically operated as a closed loop scheme using this UE feedback loop. Now, not to forget a third possibility of using multiple antennas. In the case of beamforming, an antenna array with closely spaced antenna elements is used to focus the energy in the direction of the terminal, and ideally also to null out interferers. This is achieved by adapting the amplitude and gains of each antenna element to form the beam. Beamforming is also supported in LTE, and it is especially beneficial for TD-LTE, the TDD mode, because of the reciprocity of uplink and downlink channels in TDD operation. This means that the uplink transmission from the mobile can be evaluated by the base station, and the necessary adaptations on the beam pattern in the downlink can be derived from this uplink transmission.